Okay, so up to this point, we've looked at the periodic table and we know that the elements themselves react based on what are called the valence electrons. How many electrons they can give up, as in the case of the metals, or however, or the way it works, of course, in the case of non-metals, is how many electrons they can actually accept. All right, and we've also actually seen that based on their position on the periodic table, we can actually determine what their charges are going to be. All right, so as you recall, alkali metals over on this side are in column number 1. All right, so they have one extra valence electron in their outer shell, so they will give that electron up, having a +1 charge. All right, the earth alkali metals over here are in the second column, of course, so that means that they will give up or have two valence electrons and therefore will give up those two electrons during a chemical reaction. Over on this side, of course, we have boron, which is column number 3. Has 3 electrons, has a +3 charge. Carbon is kind of in the middle, so as a result of that, it's going to be able to gain or lose electrons or actually share electrons. When we get over to this side, of course, as you recall, the column minus, or the column number 8 here, minus that one will tell us how many electrons it's going to be able to take. All right, so these ones are different because they're nonmetals. They have a tendency more to take electrons. So with that in mind, of course, nitrogen is 1, 2, 3 columns away from the noble gases, so it will be able to take 3 electrons. It's going to have a charge during a chemical reaction of -3. Oxygen, of course, 2 columns away, -2, and fluorine, 1 away, -1. And of course, we know the noble gases themselves won't actually accept or give up electrons because they're completely stable. All right, so of course, the next step in all this is to see how these elements will interact. So the first step, of course, is looking at the elements is going to be basically seeing how we're going to actually name them, because of course when we're actually dealing with compounds, it's going to give us a metal and a non-metal reacting together, exchanging electrons. So the first step, of course, is looking at our compound here and determining, of course, which elements are actually present. Well, we'll see, of course, that we've got the potassium is right there and the oxygen is right there. And simply put, all we have to do is write down the name. All right, so what's going to happen, of course, is we put down potassium. The metal always comes first, and we're going to make sure it's lowercase. All right, and then we're going to put down the first syllable of the non-metal. Okay, in this case it's oxygen, so it becomes ox. And then we add I-D-E. All right, now that is a proper compound name. Now understand, of course, that we have to put that "-ide" there because that signifies that these two elements have reacted together and they form a compound. If you put down potassium oxygen, that says we've got potassium and we've got oxygen, they haven't reacted. All right, it's fairly straightforward. All right, so we look at the second one, of course, we see there's two elements again. There's calcium, and there's iodine. So all we do is go calcium iodide. Now I know what you're going to say. This doesn't look like that's more than the first syllable. The first syllable there, it's iode. But in some cases, just like with everything else in chemistry, there seems to be exceptions to the rule. All right, now keep in mind when we're looking at the non-metals, of course, and their actual names coming out, that we're going to have a few that are going to be obvious, right, and others that are not so. For example, of course, if it was nitrogen on the end, it would be nitride. Oxygen, we already have, it would be fluoride, phosphide, sulfide, chloride, selenide, bromide, iodide, acetate. All right, so obviously there are some differences, but majority of the time, of course, you'll note that they will always have "ide" on the end. All right, now when we're actually doing the compounds themselves, taking the compound names and writing out the formulas, it's a little trickier, right? It's not quite as easy as what we just determined when we're actually finding the names. But you know what? With a little bit of practice, it comes fairly easily. So again, when we're doing this, what we're going to do is going to look at the compound, all right, and look at our periodic table. Let's pull that up for just a second here. Find our periodic table, all right, and of course, you'll note that we have calcium. Oh, calcium right there. All right, so what we're going to do is you'll note that calcium is in column number 2 right there. So that means calcium, of course, has a +2 combining capacity. So what we'll do is we'll write down the symbol, all right, and it's +2. We look at copper, or chlorine, I should say, over here, and it's column number 7, which makes it 1 away from the noble gases. It's going to have a -1 combining capacity. So we go over here and we go chlorine -1. All right, and all we're simply going to do is do what we refer to as a crisscross kind of pattern. because the calcium is going to give up 2 electrons and chlorines can only accept 1 electron each, what's going to happen is, of course, the calcium is going to give up those 2 electrons, and it's going to require 2 chlorines, each accepting 1. So in the end, all we do is do the crisscross, all right? And what we'll end up with is, and there's our formula. Calcium chloride is CaCl2. All right, and it's just as easy with any other ones. We find aluminum on our periodic table. All right, when we find that aluminum has a +3, oxygen has a -2, and again, you can figure that out just by simply looking at their position on the periodic table. And we're going to do a crisscross again. We're going to do this down to there and this down to there. So what we're going to have, of course, when we're done, is that. That's pretty easy, isn't it? Now, obviously, when we have elements that have a similar number of electrons being given up and accepted, for example, in the case of strontium oxide, strontium is Sr +2 and oxygen is -2. Now, because the strontium is giving up 2 electrons and the oxygen is taking 2 electrons, those combining capacities effectively, they cancel out. So our final formula, of course, is going to be SrO. That's pretty straightforward. All right. Now the last one we have here, all right, is a little more interesting because it's still following the same pattern. We're still doing a crisscross, and we're still looking at how many electrons are being given up and how many electrons are being accepted. But in this case, what's going to happen is, if we look at chromium on the periodic table, we're going to find, being from the middle of the table, what's called a transition metal, is that it has a variety of different combining capacities. What we have in the name here is it's going to tell us which one is actually being used, because if you look at your periodic table, you'll see that chromium has a +2, a +3, and a +6 combining capacity. All right, this number here is the Roman numeral for 6, so that means that the chromium is going to give up 6 electrons. All right, now the oxygen, as you recall from up above there, is -2. Well, if chromium is going to give up 6 electrons, and each oxygen can only accept 2 electrons, that means, of course, that we're going to need three oxygens to accept those 6 electrons. So what's going to happen is, when we do the crisscross, because these are a multiple of 2, what we're going to do is we're going to do the crisscross, all right, but then, of course, because they're both a multiple of 2, we're going to divide by 2. And that's going to give us a final outcome of CrO3. So that's fairly straightforward. Of course, these are all 2-element compounds, and things get a little more interesting when we have more elements, but that's the way it works for now.